Thank you very much. Today, I'll speak about processes, which is rather natural because of the name of our laboratory. And the question, which has a long history actually, is how to compare process behavior. When can we say that two processes are equivalent? Sorry. Yes. So I start with some very traditional stuff, very shortly, finite state machines, and then I will consider process with infinite number of states, and consider also ways of how such process can be described, and then specifically we'll speak about Petri nets and problems of comparing their behavior. So, first of all, of course, few words, why is it interesting? So when we speak about the behavior of processes, then we are to think about distributed systems which are all around us, and then so all the systems, of course, communicate, interact with each other. In this case, it is very important whether they can do some actions or not. So we abstract from data here. We just look at actions which may happen or may not happen. And when we have such interaction or behavior of an automata in some environment, then it is important for us what can these automata do, what action can it, to say, fire. And then, of course, that's why we consider formal models where we pay attention to actions. So I start with an example. So I'm not going to define what is a finite automata, finite state machine, but I'll explain. So just when we look at this example, so we have, it is represented by a finite graph. We have states represented by nodes. So just here we have two automata. So just three states here, A, B, and C. We have transitions, which are labeled by action names. And then, so just here you see that we can so do an action, and then we switch from one state to another. So here it is a beverage machine. So just we can get either tea or coffee. So you see we can insert a coin, then we switch to a new state B, and being in a state B, we can either add one more coin and then we get coffee, and the automata returns to its initial state, or for one coin we can get tea. So such a simple behavior. In classical finite automata theory, so we consider languages of finite words. So we have final states, and then words accepted by automata are just passed from initial states to final states. But when we are speaking about behavior, like here, so just we may have final states, but they are not very important here. So we can consider potentially infinite behavior. So we can consider infinite paths, and then so just such paths are also called traces. So here we have a finite state model, and it represents infinite behavior, so infinite traces, so very simple, regular traces. So to the right, there is another automata, which has maybe a bit strange behavior. So just being in the initial state A, or we can insert coin, and non-deterministically we come either to the state B prime or to the state B0 prime. And so then we do not see So to say, external observer doesn't see states, but he can see actions, what happens. So just it looks like there was coin inserted, and then it can be that, so we here, if we are in B prime state, we can add coin and get coffee or get tea immediately, but here we can't get coffee. So the behavior of this automata is somewhat different. So just non-deterministically, it may depend on many different things. So we may be lucky if we need coffee and get it, or we do not have such an opportunity. So if we speak about traces, so just we represent the behavior of such automata as a set of traces, or in other words, so languages of infinite words, then these two automata have the same behavior. So if we look what traces are possible for the left automata and what traces are possible for the right automata, they are exactly the same. So these two automata are trace equivalent. But of course, we have a feeling and understanding that so just we need another a way to describe equivalent behavior, because we don't want to consider considering these two automata so just similar. And there is a very important notion of behavior, and you see also it is what is important here is to say the branching state, so just the states where we may have a choice. So here we have a choice, and here we do not have it, and at the point where we do choice, so just that's a difference. So just here we are in the state where we come by inserting coin, but here we do not have choice, and here it is still possible. So branching is something that is important in this case. So we understand that for these two automata, external observer can notice that they do not behave the same. Then how to define an equivalence which considers two states equivalent? So just in states and system states are initial states, it's the same actually here. If they generate the same observable behavior, or external observer can't distinguish them. So to define it, it was done by Robert Milner, so just in something 81, I guess. So just there is a so-called transfer property. What does it mean? So we have two states here, M1 and M2, and we so say that they are equivalent. We have this relation L. If so, just if from M1 we can fire an action, so labeled with T, then we can fire labeled with some name. So we can fire from the second state also an action with the same name, and we come to states which are also connected with this relation. So just we suppose they should also be equivalent. And we say that if we have such a relation with such a property, we say that we have a transfer property for this relation F. So that means that actually this relation describes how we can mimic the behavior of one process by another. And then if we have that the same relation has a transfer property in both directions, then we say that it is a state bisimulation. So it is a bisimulation relation, which is very important for all these kinds of systems, because here we can so cope with branching, and we can teach it, and actually many properties depend on these, especially such things as deadlocks. So just it may be that it is too late, the choice was done before, and it is too late to make a choice to avoid a deadlock. So something like this. So we have this.
So question, what is R minus 1?
So it's just its inverse relation, both directions.
So you mean the arguments flipped?
Yes, so it means that we have one relation which connects states, and this means that if we can fire an action with some name from the first state, we can do it from the second, and vice versa. We are the same relation. If here we fire some action, then we can mimic it, simulate it from the first process.
Okay.
So it is just inverse relations.
Yeah. And so when you speak about external observer, it's one who cannot control the input, but only see what is somebody else doing. Like if you have coin machine, there might be two types of coins, two values of coins, and the external observer and does not see which coins are applied.
So we may, if we have two kinds of coins, we may have two actions, insert coin 1 or insert coin 2, you see? So we do not have states, we have only actions. And if you have a, to say, coffee machine, then when you deal with it, so just you do not see what is inside, you just see what you can do. You can either you can insert a coin or it is not allowed for some reason, and so on. Have I answered? Yep.
No, it's not completely clear. So, and sorry, I was a few minutes late. So sorry if you have to repeat. If like one machine can do the same thing as the other machine, but the other machine requires more expensive coins, are they bisimilar? Yes or no?
So we do not here we do not have real machines, we have models, and in these models we just have just finite state machines where we have actions or symbols of the alphabet or letters as in classical finite state machine theory, and that's it. And so just it depends on our way of modeling the system. We can use different actions for different coins or something like this, but then when we have a model, so we have just an alphabet of actions, and that's it. And we do not know anything about states. I mean, we do not see them. Of course, we have states here, but we compare only actions. What is happening, what is observed, that's actions. So if a relation which relates states had this transfer property, so it, in both directions, and it is called the dissimulation. And such relations have many nice properties. First of all, it can be proven that it is an equivalence, and also the union of two, the union as a set of pairs, yes, so the relation is also Bisimulation, and then there is the largest Bisimulation, and it is called Dissimilarity. So actually we say that two states are bisimilar if this pair of states belongs to some bisimulation. And of course, so state bisimilarity, so sorry for pettiness here, it's too early, but state bisimilarity is very important to check. Yes, so how can we check that two states are bisimilar? And when we speak about finite state machines, we do not have problems. Of course, everything is decidable for finite state machines. But what is surprising, actually, that trace equivalence is much more complex than bisimilarity. So bisimulation equivalence is easier to check. For finite state machines, it can be checked in polynomial time. And trace equivalence is p-space complete. And then it goes on in the same way. So just we have a trace bisimilarity becomes undecidable. So, and then how to check bisimilarity? Because so just from the definition we have that if there is a relation with this transfer property in both directions, then these two states are bisimilar. Of course, to prove that two states are bisimilar, we can just demonstrate such a relation. But to prove that they are not bisimilar, so we are to check all relations, which is not good at all. But luckily, there is a game characterization of this equivalence. And I now explain the rules of so-called Dissimulation Game. So what is it about? We have two players called attacker and defender, and we have two states for which we would like to check whether they are bisimilar or not. And then the attacker tries to prove that they are not bisimilar. So he tries to find a situation where it is not possible to mimic some move and for one process by another. And defender, of course, wants not to allow him doing it. And then soldiers, they start with this pair of processes, and the attacker may choose any element of this pair and do a step. Then the defender answers with the step from another state with the same name. And if it is okay, so they come to a new pair and continue playing in rounds. And then if some of the players can't answer to the step of the other, then he loses. And if the play is infinite, the defender wins. Then with such a play, oops, sorry, so no slide for it. So with such a play, so it can be proven that so if the defender has a universal winning strategy, then these two states are bisimilar. And if the attacker has a universal winning strategy, then they are not bisimilar. So to prove that two states are not bisimilar, we are not to check all relations, but we are to describe the universal winning strategy for the attacker, and that's fine. And that can be done for finite state machines easily, and that's why the algorithm is not so complex. So this was about finite state machines, but of course, there are also models with infinite number of states, and an example of such model, such formalism, that's PetriNet. And PetriNets, so I'll also show you an example and explain how it works. So just if you look at this part, it is like a finite automata with states S1 and S2, and B and A are action names. Just it is not like a label ascribed to an arc, but a separate node, a box for this action, and this box is called transitions. So we have nodes of two types. Local states are called places, and these action nodes are called transitions. And if we look here, so just if we have, so just, and we put tokens to mark, so just which states are active. If we have a token here in S2, then like in a classical automata, so just we can do A and switch to S1. But here we have two communicating automata. So this goes from S1, S2, S1, S2. So it is a producer. So just each time he fires B, he also puts a token here in a buffer, S3. So just the rules are, we have input places, there may be several. Here we have one. If we have a token here, we can fire B, and then we have a token plus one token in all output places. So a token here and a token here. So our producer comes to a new local state S2, and we have a new token. So added a token here in this place, which corresponds to a buffer. So then it can run the next one and add one more token. And this is a consumer. So just if now he's in this local state S4, so to fire C, to consume this item, I kept here, so just he takes two items simultaneously, so he waits until there are two tokens, and then takes two tokens and switches to S5. So it's easy to see that this buffer is not bounded, so just there may be any number of tokens, and so this is a natural thing. So just the interaction of two automatas, yes, in distributed systems. So Petri nets are very helpful for such things. But we have a situation when we have a system with infinite number of reachable states. Then what do we have in this case? So this is a definition.
Sorry, what is the
yes?
output of the previous machine?
Sorry?
So how is the output defined of this machine? So similarity of states is in terms of output.
So we do not have outputs here. It is also like an automata, but it is a distributed automata, you see. So just we have now, so a good question would be, what is a state here? So a state here is defined by a distribution of tokens. That means that we have, for each place, local state, we ascribe some number of tokens, maybe
state is clear.
Yeah.
But in the previous slides, we needed a notion of output. Right? We spoke about output of automata.
No, we have just behavior. You mean here?
Yeah, so what is this L in the previous thing? So you had definition of this.
So you mean in finite state machine?
Yeah, so there were output tea and coffee.
No, it is the name of action.
Okay, and what is L?
It is just the name of action here.
On the next slide, what is L?
The next slide? Where?
Yeah, so there is, slide 4.
Slide 4. So L is the name of action. So just here, name of action is coin or coffee.
Okay.
Yeah.
Sorry
so because we just define graph, so we have this arc and this arc. We may have several arcs with the same label. Yeah. So L is label, name of action, but we have two different arcs here.
So U is arc and L of U is the name of the arc.
Yes.
Okay, sorry.
Yes.
Okay.
This is the transition. Yes, and it is the name of this transition. So what do we see? But of course, they are different transitions because they change differently in the states of the system in some sense. Then we have these Petri nets with so just also can be represented by finite graph, two types of nodes, local states, places, and actions, transitions. And it is a bipartite graph, and we have these states which are described by so-called markings when we put tokens into places, any number of tokens. And then we can interpret these states as multi-sets of places. So just if we have to say k tokens in a place P, that means that we have k copies of this place, yes, in this multiset. So we can, of course, study Bisimulation equivalence for Petri nets. So just states are marking, so it is marking Bisimulation. And it is a very important notion, but for Petri nets, for classical Petri nets, so it's just a model which is not Turing power at all, and many problems are decidable for Petri nets, for instance, reachability, but marking Bisimulation is undecidable for Petri nets, and it was proved by Petr Jankar in 1994. So it is a well-known result.
Sorry. So in slide 4, we had labels of arcs, and now the labels, is it true that is equal to the names of the transition? So
yes,
it was
exactly.
A, B, C, D?
Exactly.
Okay, and so can you have the same transition several times in different places of your graph?
So when we have so I will return to this example.
Yeah, so here we have four different names.
When we describe a model, then we have set of places, set of transitions, and labels for these transitions, which are names of actions.
So is it allowed to replace C by A? So the same transition name appears twice?
The same name, yes. The same label, yes.
Just to double check. Okay,
yes.
I got it. Yeah.
Exactly. So we have this undecidability result, and that means that, of course, the same gain characterization is works. So just to check whether two states are similar or not, we are to give a winning strategy either for attacker or defender, but there is no universal weight constructed. That's the case.
And so you do it by simulation of counter machines, like Minsky, one counter.
Yes.
Okay.
Yes. And then, so of course, we spoke about Petri nets and not looked at so just exact definition of their semantics, but actually for Petri nets and for other systems with finite or infinite reachability set, we so just what is sorry. So just we speak about so-called label transition systems. This is a universal way to represent systems behavior. And label transition system, so just it looks almost like a finite state machine, but it may be infinite. That's the case. So it is a finite or infinite graph where we have a set of states, nodes, actions, labeling, arcs, and also we have names for these arcs, labels, which so give names to our transitions. So I'll give an example for Petri nets to explain what happens. So here we have our Petri net, and then we encode markings as vectors. So this means one token in the first place, no tokens in the second, and so on. There are 1, 2, 3, 4, 5 places. So initial state is one token in S1 and one in S4. Yeah, exactly. Then B can fire, and that's the only transition which can fire now, because for C we do not have tokens to consume. So we come to a new marking, then A can fire. Yes, A can fire. We return to this marking, then once more B fires, and so on. And this is just an initial fragment of this label transition system, which represent Petri net behavior. So what do we have? We have a compact finite model, but it has infinite number of reachable states. And then we can represent it with such a label transition systems. And then each trace here is a path from the initial state, and so going infinitely long. So, of course, not only Petri nets can be used for describing the behavior of such systems, and there are another ways to represent such models. And one more way is to use, to say, algebraic approach. So just to describe these processes like algebraic expressions, and then to have rules which define transitions. So it is like Tom rewrite systems, actually. So first of all, we describe define process expressions, and we have some alphabet of actions. Yes, and then this is a definition. You see, it is quite simple. So just it is an atomic action, or there is a special invisible action. Also, we have sequential composition. So just doing here, E is a process, expression for a process, then so do E and then once more, and this is a parallel composition. So then we suppose that so this invisible action, so it's like so zero or element, and we have also that our parallel composition is commutative. So such a simple language for describing expressions and then to define semantics, we have rules. And rules, so just we have to define a system. We have initial expression, and also we have transitions which are represented in the form as a rewrite rules. So just we have this in expression. That means that we substitute E2 for E1. Yeah. So for a sub-expression E1, we substitute E2. And then the rules are quite natural. So if we have such a firing, then we can apply it. Yes, of course, for parallel composition, it means that if for E1 we can fire A and we then get E1 prime, then so just in this parallel composition, we can do this substitution, and E2 is still the same. So just they are independent, they are concurrent. So this is symmetric. And for sequential composition, we can substitute only in the first component of this composition. And that's actually rather clear, because so just if for some reason this will not end, so just we will not come to it. But just formally, such a very simple writing systems which describes the behavior of the system. And then we can construct label transition systems which describe the behavior of such process rewrite system. And it will have, so just states are expressions. And then if we have a transition which so transforms one expression to another, we have an arc between these states, and we have may have infinite number of reachable states. So this is a rather general way of representing processes. And what is important, this system is not Turing complete. So it is also rather restricted, and reachability is decidable for such processes. So what is interesting with this way of representing the behavior? So we can consider different subclasses of such systems when we restrict the form of our expressions. So we'll denote, we'll write one for just atomic tone, so just an action, and that's it. As these are tomes which are constructed only with sequential composition. P are atoms and their parallel composition, and G are general atoms. And then we can consider systems, and we define it as follows. So this means that we use rules where the left and right parts are both atomic tones. And these are just finite state machines. So it's easy to see. We have just states are described by atomic expressions. Yes, if we consider systems where we have just left part of our rules are atomic tones, and here we have parallel composition, then we get so-called there are many formalisms studied already before that. So we have special kind of process algebra, or it is equivalent to context-free Petri nets. And context-free Petri nets are Petri nets where all transitions have just one input place. And then if we consider, so here we have also atomic to the left and sequential to the right. This is another class of process algebra, which is called BPA. So it can be defined this way, actually. And if we have parallel composition, both left and right components of our rules, these are exactly Petri nets, and SS are push-down automata. So that's really very interesting. So we have a universal representation of all these well-known models. So we can describe it as a hierarchy. So just here we have finite state machines. Adding here parallel composition, we have so this context-free Petri nets or BPP algebra. Here we have BPA algebra. Here we have Petri nets. This is push-down automata. And for these, we do not have, so just previously they were not described. So yes, but these are just classical things. So we have such a hierarchy, and for all these classes, so they are less than Turing power, and for instance, reachability is decidable for them. But we are looking at Dissimilarity, Dissimulation equivalence. And if we look at this hierarchy, we'll have such a picture. So for finite state machines, Bisimilarity is decidable. Also for context-free Petri nets. For Petri nets, red means undecidable, and of course upper classes. Here also for BPA and push-down automata, it is decidable. And these two gray classes, it is an open question. So such a nice classification. And then, of course, it is very interesting to understand so just where actually this border lie. And we have exact border here, you see. So just for context-free Petri nets, it is decidable. For classical Petri nets, not decidable. So we'll look at this border and we'll study, so just what can we see here. So, and for that, we'll have a bit another way of looking at Petri nets. And so just we'll call it resource perspective. So just when we look at Petri nets tokens, so just residing in places, they can be considered as resources which are consumed or produced by transition firings. So sometimes, like, so just in our example, there was a buffer and there was some resource produced and consumed. And then, so just there is a way of looking at these, so just to give interpretation as resources for markings of Petri nets or parts of their markings, sub-markings. And then here is an example which illustrates it. So just we have a Petri net. So it is a shop where we can buy, to say, some candy. And then, so just we have, this is a place for coins of 10 cents, 5 cents. And then, so just this candy costs 20 cents. So just either you see, these are the same labels because it means buying this candy. We can do it for 2 10-cent coins or for 4 5-cent coins or 1 cent and 2 5. All variants are true. And then, of course, we then understand that though 10 cents are not enough for buying candy, we need 20. But we, of course, can note that 10 cents is so equivalent to 2 5-cent coins. Yeah. So, and then we would like to consider such an equivalence, which we call resource equivalence. And what is the meaning exactly of it? It means that we can use 2 5-cent coins in any marking for 1 10-cent coin. Yeah, in this example. So then we call some, to say, sub-markings, they look like general markings. We call them equivalent resources if we can substitute one resource for another in any marking. And we have the same behavior, the same up to Bisimulation. So why do we need it? Of course, so just when we can use it for state space reduction, for reduction of models, for adaptive control, and so on. So just I think it is clear, but also it is interesting to look at it because it is a relation which so just which we are looking for, so just we would like to find something that is decidable. Yeah. Then, so just looking at this resource equivalence, so we are to mention that there was a special case of such equivalence called place fusion, defined by Philip Schnobelin and Natalia Sidorova. And so just it was defined as so we can, with 2 places are equivalent in this sense if we can transfer a token from one to another without changing the observed behavior. No? And that means actually that these two places can be fused in the model. But it was proved that place fusion is undecidable. And then when we define resources, we say that two resources are similar if substituting one resource for another in any reachable marking, so doesn't change its observable behavior. Then, like here in our example, we can change 1 10-cent coin for 2 coins of 5 cents. But of course, so just place fusion is a special case actually of this resource similarity. So it is also, it turns that it is also undecidable. And still, this resource similarity has nice properties. First of all, it is a narrowing of state bisimulation, and also it is it is a congruence. And so just why we are interested in congruences, because so just this context-free, for context-free Petri nets, Bisimulation is a congruence. We have just one input place, so we can just substitute for atomic subtom, yes, each time. And then it is a congruence. And then we are looking for congruences because we believe that there should be a candidate to get some decidable narrowing of marking Bisimulation for Petri nets. So just still, it is undecidable. Good news are that, and that's also because it is a congruence. So we have proven that this resource similarity has a finite additive transitive basis. What does it mean? So this relation is closed under transitivity, and also it is closed under addition of resources because it is a congruence. So we just can, these are multisets. So we have that if we have two pairs of equivalent of similar resources, then we can just add them and get a similar resource. So they have finite representation, finite basis, but it is not possible to compute this basis. So then we look for something which is decidable, and then we define resource bisimulation, and it is defined like this. So we say that an equivalence is a resource bisimulation if its additive transitive closure is a marking bisimulation. So it is like a base. So just we construct a closure and we get everything. And we are looking for such a base, which is also a bisimulation itself, of course. Then we also have nice properties for this resource bisimulation. So if we have, so it is closed under union. So there is the largest resource bisimulation, and it is called resource bisimilarity. And if we have two bisimilar resources, they are also bisimilar as markings. So it is a narrowing of marking bisimulation. Then it is a congruence. It has additive transitive basis, and also it has it can be characterized by a transfer property, but of a special kind of transfer property, which is called resource transfer property. So what is the difference? So here, when we have a resource and we want to fire T, an action, then we can add resources, so tokens, which we need to fire T. So for any transition, we have some resource, and then we can add what is needed, and we have a transition. And to fire this transition, maybe we do not have enough resources, and we add what we need. And then to answer, we can so just to say this is an attacker and this is a defender. The defender may use these added resources as well. He has what he has, but what was added, he also can use it. And then we have such a transfer property which allows to be more flexible in some sense. And then we have this characterization of resource dissimulation, which says that a resource dissimulation is a relation which satisfies the resource transfer property in both directions. So just we have another transfer property which is more strict, and then we have a narrowing of our resource dissimulation. So what do we have now? We have that a relation of resource similarity, which is a congruence, and it strengthens marking bisimilarity. We have resource bisimulation, which is also a marking bisimulation, and it is a congruence, and also it strengthens resource similarity. And then we define the resource bisimilarity as the largest resource bisimulation. So if we compare these two, three equivalences, so marking bisimulation, resource similarity, and resource bisimilarity, then they coincide for context-free Petri nets, and we have strict inclusion for classical Petri nets. So there are examples showing that, so this is an example when we have resource similarity, showing that resource similarity doesn't coincide with marking bisimilarity, and another example which distinguishes resource similarity and resource bisimilarity. I'm afraid I do not have time to explain details, so you just believe me. And we can also define resource bisimilarity game, almost the same, except that we can now, the attacker chooses a resource and it can fire any action, because so just if he needs to add something, he can use it. Then the defender also uses what was added. And finally, so just this is a characterization about winning strategies, similar to the classical case, but good news is that resource bisimilarity is decidable. That's the recent result, and it's really interesting. So we could say that, oh, well, it is a congruence, but resource similarity is also a congruence, but it is undecidable. So we found this body between decidability and undecidability in this sense. So algorithm, so just the idea uses tableau methods, which was used for proving decidability of bisimulation equivalence for context-free Petri nets. But here, of course, we do need to adapt it to resource transfer property and also to prove some additional properties to show that this construction works. And so it is, of course, this algorithm takes much resources. So just complexity is not known, but for context-free Petri nets, this problem is piece-based complete. And trace equivalence is undecidable for all infinite systems. So, of course, also we can check this resource transfer property for finite relations, and that means that we can construct approximation also for this relation. But so just we don't know where to stop, because if we knew, we could compute this additive transitive basis. Still, this is an open problem whether the basis can be effectively computed. So the case is that though the relation is decidable, and we know that there is a finite basis which represents this infinite relation, so it is not known how to compute this basis and even whether it is computable. So this is an illustration showing that if we approximate, we can't say that when we come to some stabilization, that's it. It's not enough. And now, so just short conclusions. So we were discussing decidability bodies for bisimulation equivalence. And for that, we considered congruent restrictions of bisimulation equivalences for Petri nets. Because so just for congruent subclass of Petri nets, yes, it is decidable. For classical Petri nets, not. So just we were looking for some more coarse border. So we've defined two equivalences, resource similarity and resource bisimilarity. So both formalize replacing a resource, one resource by another without changing the observable process behavior. And then so just both are congruences. So bisimilarity is the largest congruence included in the largest sorry, I should say that it is the largest largest congruence and closed under so which is a bisimulation itself, the largest congruent bisimulation included in one. And the second is the largest congruence included is classical bisimulation equivalence. Both of them are finitely based, but the first is undecidable and the second is decidable. And of course, for the undecidable relation we can't compute its additive transitive basis, but computing it for the decidable relation is an open problem. So sorry for a bit being too quick maybe at the end.
Okay, yeah, thank you very much. There have already been quite some questions during the talk, but maybe there are more. So other questions?
Yes, these are further research, and so there is a preprint with these results. So it was done together with Vladimir Bashkin from Yaroslavl University and Petri Shankar from Czechia.
For me, it was hard to understand the second resource bisimilarity. Around slide 27, it became difficult. It was very fast.
Resource bisimilarity, so it is a congruent narrowing, which is a bisimulation itself. Similarity is not a bisimulation. Similarity is, so just we have a bisimulation relation, then we consider a subrelation, which is a congruency, which is congruent, yes? But this congruent relation may be not a bisimulation itself. So it is a bisimulation for this context-free Petri nets. So for context-free Petri nets, all these three relations coincide. But generally, so it is not a bisimulation. So a transfer property is not valid for it. But then we define, we narrow it to a congruence relation, which is bisimulation itself. It is not the largest bisimulation, but it is a bisimulation. So then we have this resource bisimilarity.
So you showed a diagram, I think around slide 20, with two open questions. So there was all this hierarchy of four process algebras. So these open questions, they're considered important, or
So of course. So it's of course.
Yeah. So the next slide, 16.
They are open for a long time already. So of course it was not easy to. Of course it was so just in late 80s or 90s. It was proved that Petri nets for Petri nets it is undecidable. So this construction for decidability for this context-free Petri nets, I may be mistaken with this. I think also something like the end of the previous century. But first, it was a very complicated proof. Then there were new proofs, and then there was this tableau method, which now it is possible to tell it to, of course, not to students, maybe immediately, or to mathematicians, students, so just to students in logics, at least. And it is very nice. So just not easy, because so it uses two special well quasi orderings on states, and then so just to show that this tree this also just it's rather complicated. And for this it was and then for this with sequential for PDA, it was of course later, and it is even a more complicated proof.
But my question is not to speak very long about how complicated it is. The question I wanted to ask is this class PAD as G and PA1G, are they somehow natural classes?
So they are natural as process algebra, yeah. So just it is a very, very simple natural operations, composition and parallel composition, so sequential and parallel composition. So we have expressions and we have natural rules to describe their behavior. So we can, when we construct model, we can either use just automata-based representation like Petri nets or communicating automata, or we can use algebraic representation. And the philosophy is that we have an algebraic expression which describes possible behavior. So the state is what can be done from this state. So this expression describes possible behaviors. And of course, it is a nice way to deal with. So we can prove something, we can do verification, we may describe formally the behavior of communicating processes, which is very important. But when we have this sequential together with parallel, so it becomes quite complicated. Yeah.
My question is, coming back to the standard, well-known problem, decidability of Petri nets, do you have some nice, transparent procedure, a proof that basic problem is decidable?
So it depends on the problem. So if the problem is boundedness, yes, easily. So easy
I understand.
to
The
but
problem
if it is a reachability,
yes.
So I don't know. So just and to say that this algorithm, so this hierarchy, it was constructed, and so just for this hierarchy, it is proved that reachability is decidable. And actually, it is a somehow generalization of this proof from Petri nets to these more general systems. So just the idea is the same. It is rather complicated, and to say truth, I didn't so just look into details. So just. So you need time and efforts to go through it. So just no need. So just I know that it can be done.
Yeah, thanks.
So sorry, can you repeat briefly for the reachability problem? The diagram is the same.
For the reachability problem, so for all these classes, reachability is decidable.
Okay.
So it is these are nice classes, you see. Reachability is decidable for all these classes.
Okay, thanks.